Welcome everybody. Thanks for coming along. I was approached some months ago when they asked me if I might be able to offer some training to the N8 CR group, and I offered this and they took me up. So here we are. We're going to be looking over 4 weeks at some basic machine learning methods. So the basic structure of the course is I've made this website which you can go to, and you'll see that for each week there's going to be one online worksheet in the form of an IPython notebook. You can access them whenever you like. So don't fret about taking notes or anything like that, because it'll all be available there at the end. So I'll just share the screen so you can see my view of that. So if you click on that link, you should see something like what I've got on my screen now at the moment. This machine learning for humanists at the top, a list of files, and you'll see there's session 1, session 2, session 3, session 4, and then down here in the README section, you'll see that there's a different link to session 1. So if I can just ask everyone to click on that link, this specific link, it's going to open the notebook in Google's Colab system. I don't know if any of you are familiar with this, but if you get into machine learning, you'll probably spend a fair bit of time on Google Colab. It's a free online system where you can test Python code, and it comes with all of the required libraries for machine learning pre-installed. And Google actually provides you with a remarkably large amount of computing power behind this. Google Colab is running on a server. Okay, so if I could ask everyone to click on the link and get something like what my screen on screen. I'd like you to do this first, because it may ask you to log in if you don't have a Google account. I'm not sure. Mine just is automatically logged in because I'm using Chrome. So perhaps none of you will have that login. And at the top, you'll see where mine says RAM and disk up here at the top right. If you see the word connect, could you just click connect? And that'll start the computer over in Google's data center so that you have that available. So just while you're doing that, I'll begin with a bit more of an actual introduction. So I'm Michael Falk. I'm a lecturer in 18th century literature at the University of Kent. And in my own work, I do quite a bit of various kinds of machine learning and statistical analysis of literary texts. So that's where I'm coming from. And the techniques I'm going to be showing you in this course are all going to be based on analyzing text. But it should be noted that if you come from another discipline, there are, of course, machine learning techniques that apply to sound or to image. Some very famous machine learning algorithms do, and I'll mention some at the end. But for the sake of making the course digestible, we're just going to focus on one application, which is machine learning as applied to text. Lots of people are a bit intimidated by machine learning because, mathematically speaking, it's relatively complex, and if you get into the nitty-gritty of the algorithms, it often takes you quite far from your disciplinary background if you're a humanist like me. Yeah. But actually, from a programming perspective, it's very simple, because there's these frameworks that have been developed which allow you to very quickly select a model and apply it to some data and get the results out with only a few lines of code. A lot of the code is the same in Python or in R. When you move into deep learning, which we're going to spend weeks 3 and 4 on, the framework I'm going to show you is TensorFlow for the back end that runs the whole thing. But the sort of syntax you use, the words you write, the code you write, is in Keras. And that actually is also implemented in R. So the code is more or less the same in both. A few differences of syntax, but the basic pattern of the code is the same. So you shouldn't have any trouble moving from Python to R. And in fact, if you want, there's a good R cheat sheet that shows you how to use Keras in R. So I can direct you to that if you remind me. And that should make it relatively easy for you to port what we learn here over into R. But this also leads me to another point, which is that in this course, although I said in the online description that people should come with some coding knowledge, because I didn't want to spend the first week just introducing you to Python, the coding we're going to be doing is not it's not very difficult coding. There's not going to be any complex issue where you have to write some elegant code that performs a set of steps in the right way to solve the problem. It's much more easy than that. I'm going to give you some simple templates and you're just going to copy them. It's very simple coding. So I hope that reassures everyone. And if you've managed to open the IPython notebook, you'll see that that's the first thing I address, the relationship between machine learning and artificial intelligence. And yes, by learning a bit about some of the main machine learning algorithms, that will tell you a lot about actual AI systems that exist today and that affect our lives. And indeed, some of the algorithms we look at are very similar to the ones that are used to, for instance, pilot autonomous vehicles, to recognize faces, these sorts of things. Okay, so to begin with, the first section for today is to introduce you to what exactly machine learning is and how it's related to this other famous topic of artificial intelligence. So as I say there on the screen, basically the relationship between these two things is that machine learning is a series of practical algorithms which try to achieve AI. That's the best way of thinking about it. AI is a goal or an aspiration, you know, to try and make computers intelligent or make machines intelligent. They don't have to be computers, but, you know, artificially create intelligence. Machine learning is a certain kind of computer programming, which these days is considered the most likely way of achieving artificial intelligence. So what are these algorithms exactly? Basically, it's just where instead of writing a traditional computer program where the programmer explicitly tells the computer every step to do and then just gets the computer to do it, that's how a traditional program works. In machine learning, you instead give the computer some data and you write a program that lets the computer extract some information from the data. So in a sense, the computer is learning what to do from the data. But of course, the human programmer is the one who knows what the data is and has set up the computer so it's capable of interpreting the data in the proper way. It doesn't really, machine learning algorithms are not very independent of human beings. And if you ever read anything in the press about how frightening modern AI is, it's rubbish. There's really nothing frightening about it. The only people who think it's frightening are billionaires who have a lot of money invested in it and want to create a bit of a sensation. Or, you know, science fiction novelists who, again, want a little bit of sensation to add something to their flights of imagination. To begin though, I just want to mention that machine learning was not always the primary paradigm of AI research. That actually, it only really became popular in the 90s and really dominant in the noughties. In the first phase of artificial intelligence research after the Second World War, there was actually a very different approach to artificial intelligence research, which I've tried to give you an example of in this code block here. So this older form of artificial intelligence was called symbolic AI. And the idea of symbolic AI was this: the people thought, who were investigating intelligence, that what makes humans intelligent is the power of reasoning. It's our ability as humans to form concepts and then apply them to the world in, you know, and relate them to one another. That's what makes humans intelligent, the power of reason. And so early research in AI was very focused on trying to give computers the power to perform abstract reasoning. And the way this was normally done was that AI researchers would try to find a way of representing human knowledge inside a machine. So they would find a way of representing concepts in a machine and representing relationships between those concepts. And then the idea was, if you gave a machine enough concepts, a rich enough ontology, and a rich enough way of connecting those concepts together, then the machine would become capable of reasoning. So here's just a little example, this bit of code. This really doesn't resemble very closely any real symbolic AI program. It was just me trying to indicate how this might work in Python, which isn't really built for symbolic AI. You can't really do symbolic AI properly in Python. You need other frameworks, but nonetheless, this is sort of an example of what you might do. So I've provided my computer with a really complex ontology. It knows about two different things in the world. It knows that there is something called animals. There's such a thing as an animal, And one thing an animal is mortal. An animal is mortal. That's the one thing it knows about animals, is that they're mortal. It doesn't know anything else about them, but it knows that they're mortal. And there's a second thing that exists, which is called a human. And you'll see here in the brackets that I've told Python, actually humans are a subset of animal. All humans fall into the class animal. But as well as having whatever properties animal has, human has these two other properties. Humans have 4 limbs and they're bipedal, at least in general. Obviously not all humans have 4 limbs and not all humans are bipedal, but you know, there's no way. This is one of the problems with symbolic AI. There's actually no way of really coming up with a final definition of human that works. You know, there's that famous example from Aristotle, is that a human is a non-feathered biped. I mean, so are the dinosaurs. It doesn't really work. Okay, so we've provided the computer with an ontology, a set of concepts, and also with some way of relating them to one another. So in this case, there's one particular relationship, which is that a human is a type of animal. Then how could the computer do some reasoning? Okay, well, I've defined here a little function. The function's called isIt. And this is the function the computer can use to ask, is this human something? Is this animal something? So when I use this function, when the computer uses this function, it applies it to some being that exists in the world, and it asks whether that being has a certain property. So, for example, is this particular person mortal? Okay, so that would be the isIt function applied to some particular person, and you're asking whether that person has the property mortal. Don't worry too much about this code here. But basically, we've got the computer understands there's 2 things in the world, and it's capable of asking this question, which is, does the thing that you've just presented me with have the property that you're asking about? So here's how we could apply this ontology in practice. I'm going to create a new thing called Socrates. And Socrates is a human. So I've created a new human called Socrates. And then I ask, is it Socrates mortal? Which is basically just asking, is Socrates mortal? Does Socrates have the property mortal? Okay, and if I execute this cell by pressing Control Enter, that's how you execute a cell in Jupyter Notebooks, if you don't know, or by pressing this little play icon. If I execute that, you'll see it says true. I've given the computer enough information and enough reasoning power that when I tell it that Socrates is a human, it can work out that that means Socrates is mortal. So this is an example of how symbolic AI was supposed to work. That you try and give the computer a really rich set of concepts and then ask it to do some reasoning on those concepts. And the initial dream of AI was, if you did enough of this, you'd actually be able to build an intelligent machine. But during the so-called AI winter of the 1980s, AI researchers completely lost faith in this approach to AI programming, pretty much. So here, the way I've written this program, because I've said that human is a type of animal, okay, it automatically inherits the property that it's mortal, which is how come when I tell the computer Socrates is a human, it then knows that Socrates is mortal. But of course, I could actually change this. I could say that Socrates, I could actually just override that, like so. And now it's false that Socrates is immortal because I've just made him immortal by overriding it. So yeah, there is some flexibility, but generally it's generally true. The early applications of this symbolic AI in so-called expert systems, they were found to be very brittle and not very adaptable to new situations, and it proved extremely difficult to create a rich enough ontology to actually work in the real world. Humans are very good at encountering many things and coming up with many concepts. Yeah, I mean, you could put moral principles in there. There's no reason you can't put good or just or evil into your ontology and then provide rules for reasoning about it. You know, many people think that moral reasoning is possible and so could be explicitly put in the program. But if you're talking about like the sort of sponginess of human reasoning or the way we flexibly combine different domains of knowledge, that's quite hard to do, absolutely. we're not going to talk about symbolic AI for the rest of the course because obviously this is about machine learning. But in the 90s, basically a couple of things happened that revived interest in AI research and put it on a new track. The first was that much more data was available. So that made it possible to think, okay, maybe we can actually get the computer to learn from data the way a human does. We learn empirically, generally, most of the things through our senses. Maybe we can do something like that for a computer. A second point was that there was a change in computing architecture. There was the development of so-called parallel processing. So if you in your computer now, you have an Intel quad-core processor, that means there's 4 little processors in there. It can do 4 things simultaneously, which means in principle, it could work 4 times more quickly than an old-fashioned processor that could just do one thing at a time. New kinds of chip were developed that were even more parallel. So if in your computer you have a graphics card, if you're a gamer and you have a graphics card doesn't just have 4 processors in it. It actually has thousands of very small, not very powerful processors, but many thousands of them, which is actually ideal for doing computer graphics, which requires many, many, many simple calculations rather than a smaller number of complex calculations. And due to some aspects of linear algebra, this mathematics that I won't get into, which runs a lot of machine learning algorithms, it meant that actually with modern computers that have a smaller number of weaker processors in them, it's actually very possible to run these big machine learning algorithms in a way that old computers simply could not handle. So something that might have taken an old computer literally a million years to do can now be done in a few hours on a modern supercomputer. So these 2 things made it possible to do machine learning. And then there was a series of breakthroughs with machine learning. And it's now colonized all aspects of our lives. You know, Netflix's recommender algorithm, the thing on Google that completes your emails for you, Facebook recognizing your face, all this, it's run by machine learning. So it's everywhere. But just before we move on, I do want to draw your attention to this project, which there's a link to in the notebook, called Psych, which is the longest running and most famous symbolic AI project in the world. And they are actually trying to represent the whole of common sense in that explicit fashion that I just showed you. So if you click on this platform and scroll down, they say, see here, they say they have this thing, the knowledge base, combined with an inference engine. And they claim that this knowledge base can more or less represent common sense in explicit propositions, and the inference engine can do all sorts of reasoning on it. And if you scroll down, I mean, it's a private company that's trying to sell your products. So they obviously try and make this sound really good. But they claim to have 40,000 plus predicates. So they're like things you can use to connect concepts to one another. 1.5 million concepts in their knowledge base. And as a starting point for connecting those concepts together to form a system of knowledge, they've created 25 million axioms, you know, which might express something like, I don't know, if something's mortal, it will die in less than 100 years or something. I'm not sure what their axioms are, but they claim to have done a whole lot of the basic reasoning already. So there's a whole basis of reasoning that's already been done, on top of which the computer can then reason. Which is why they then say there's trillions of implicit axioms, which could be derived by combining some of these 25 million explicitly stated ones. Now, actually, one thing that's interesting is it's a long-running symbolic AI project, but actually, they also use machine learning. So there's machine learning on top of the symbolic AI. And a lot of people think that as machine learning's kind of seeming to reach some limits, there's some things that machine learning just doesn't seem to quite be able to do. For instance, safely pilot an autonomous vehicle in traffic. Just probably machine learning on its own is never going to get there, actually, for various reasons. Some people think that machine learning plus this good old-fashioned AI, as it's sometimes called, that combination might be what makes it possible for computers to exhibit the same kind of flexible, intelligent behavior that animals can. Just execute this cell. Okay, so you can either click the little play icon or you can press Command Enter or Control Enter on a Mac, or Control Enter on a Windows, it'll give you a message saying this notebook's not from Google. So do you sure you want to run it? You can run it. You can trust me. I haven't put any malicious code in there. And you can see all the code on the screen. There's no way I could hide a virus here. You know, it's pretty basic code. So just click run anyway when it says that, and put in the chat if anything didn't work. Okay, I've given you here some examples of some famous machine learning algorithms today. Google Translate is obviously a very famous machine learning system. Google has collected a huge corpus of text in about 50 languages. And the way that the machine learns to translate it, the programmers don't program any linguistic or grammatical rules at all. It's all machine learning, Google Translate. And basically what the computer is given is a series of sentences in one language and matched sentences in English. They always learn to translate to and from English. English is the so-called intermediate language. And the computer simply learns to go from the original language to the translation using a so-called encoder-decoder network. And then it can translate from any language to another by translating first into English and then into the next language. And if you've ever used Google Translate, as I'm sure many of you have, you'll know that there's actually a feature for users to tell the machine when it's got it wrong. And then it'll learn from what you said. Every time you do that, you're actually giving Google free data, which they then use to improve Google Translate, which of course they then provide to you for free. So I guess it's a fair trade, isn't it? Another one, which you might have heard of, is the GPT-3 language model. This one got a lot of press coverage. It's basically a big text generation model. It's got 175 billion parameters. So basically, it's not a very intelligent system. They just made a huge system and gave it heaps of data. And as a result, it can generate text that's ostensibly coherent. If you ever read any fearsome press coverage about it, I wouldn't pay any attention to it at all. This computer can generate text that seems coherent, but it has absolutely no idea what it's talking about or any conception of when certain language might be relevant to a certain context. So it can just gibber on nonsense that appears to be English, essentially, but it does produce very compelling nonsense. And then there's the Deep Dream Generator for any art historians or artists we have here. You might have heard of the Deep Dream Generator. This is actually a special thing where it actually runs an AI software backwards. So it takes software that was built to recognize what's in an image, and instead of asking the software, what do you think is in that image? It says to the software, manipulate that image to make it look even more like what you think it looks like. And then, anyway, it can look a bit weird. You know, this software obviously thought that there were lots of eyes in Van Gogh's Picture of the Night, you know, and little sort of animal faces, which is not surprising because the software used to generate this image was trained to recognize images of animals. So when you use it to manipulate an image, it thinks it sees animals everywhere, which is, you know, kind of fun. So there's some famous machine learning algorithms you might have heard of, but really your whole life is permeated by machine learning all the time these days. So I've said that machine learning is a whole family of algorithms. There's heaps of them, and we're going to be looking at 3 later on. Next week, we're going to be looking at latent Dirichlet allocation, which is a popular topic modeling algorithm. The week after that, we're going to be looking at recurrent neural networks, which can be used to model and generate text. And the final week, we're going to look at so-called skipgram models, which can be used to create word vectors, which basically tries to represent the meanings of words as a set of numbers by comparing which words tend to appear near one another. That's the point of word vectors, and you use a skipgram model to do that. So we're going to look at all these different algorithms, but this week my aim is more to give you a map of what sorts of algorithms there are. So to begin with, here are 2 crucial distinctions that underlie machine learning. One is the difference between supervised and unsupervised learning. So So basically, the difference is this. You can either, for so-called supervised machine learning problems, you give the machine the input data and you also give it the answers. And you tell the machine, can you find a way of getting from the input data to the answer? That's a supervised problem. You give it both the raw data and the answers and it learns to predict the answers given the data you've given it. The unsupervised approach, you just give it the data without the answers, and you ask it, computer, can you find some structure in this data? If you've ever heard of cluster analysis, or clustering, that's an example of an unsupervised method. So you've just got a whole mass of data and you say to the computer, please find some structure. Now, as it happens, in future weeks, we're basically going to be looking at unsupervised learning, not supervised. So we're going to look at techniques where you don't have the answer and you get the computer to try and infer the structure. In humanities, unsupervised methods are normally the most useful. In other fields, supervised methods tend to be the most useful. Like for a really obvious example is economics. Okay, so in economics, you have the problem that you have a lot of data about the economy, and then you have some endpoints that you want to predict. For example, economic growth. I want to know how much the economy will grow next year. That's such a fiendishly complex question, isn't it? I mean, how complex is an economy? And I can measure all these things about it, you know, like inflation and unemployment rate and investment and so on. But these are very crude measurements when you think about what the economy is. But what you can do is you can get a time series. You can get the level of inflation, unemployment, etc., every year for the last 100 years. And you can get the GDP growth that year for the last 100 years. And you can tell the computer, okay, could you look at all that information and the GDP growth and learn to predict the GDP growth based on the other information? And then that model is now a predictive model, and you could use it to try and guess what GDP might be next year. And you could adjust those different parameters. What if we put up the interest rate? How would that affect economic growth according to this model? So that's an example of a supervised model where you have the answer and you also have the input data and you want to get a bridge between them. There are some areas of humanities where that's useful. Like obviously if you're in business history, something like that, like I've just described, might actually be very useful. Or if you're in art history and you want to determine who painted a painting, or similarly, you want to determine the authorship of a novel or the composership of a piece of music, you might use a supervised method where you first give the computer a series of examples where you know who wrote it, and then the computer learns to predict who wrote the thing or painted the thing, and then you give it the new piece that you don't know the author of, and the computer tries to tell you who it is. That might be a place where you could use a supervised method. But normally in the humanities, we're after something different, aren't we? We've got, you know, a bunch of old newspaper articles, or we've got a linguistic corpus, or we've got, you know, a database of 3D images of sculptures or whatever else. And we want to say, well, what can I find here? You know, how are these things put together? So that's why unsupervised methods tend to be the most useful. The other key distinction that I want to introduce before we get into our first practical example is the difference between training and inference. So you could translate this as training means learning and inference means application. That would be another way of using it. But the terms that are always used in the literature are training and inference. So what are these two phases? Training is when you get your chosen model that you're going to create. Okay, machine learning always creates a model that the computer then uses to understand the world. You've chosen the model. The training phase is when you expose that model to the training data and you instruct the computer to improve the model based on the data. So that's when the computer is learning. The inference phase is when you actually then get that model and apply it to something. In practice, these two phases can be very hard to distinguish for two reasons. Number one, the training algorithm often involves the same analysis as the inference algorithm. For example, the most popular machine learning algorithm of all is so-called backpropagation, which runs neural networks. And we're going to be looking at that in weeks 3 and 4. When you do backpropagation, what happens is that your system, your neural network, looks at the input image or text or whatever, predicts what it thinks that thing is, sees if it was right or wrong, and then the error, the wrongness of it propagates back through the network. In other words, the computer then adjusts all its internal parameters to make up for the error in its previous prediction. Then it makes another prediction. So it predicts and back propagates, corrects, predicts, corrects, predicts, corrects. And then, of course, when you actually apply the neural network in practice, you just drop the correction part and you just do the predict. Or you might keep the prediction, the correction part. You know, that's what Facebook does. It constantly updates its model of your preferences every time you pause on an ad in your newsfeed or skip over it. So the training is ongoing, and it's along with the inference. They're applying the algorithm all the time to serve you ads, and they're also updating the algorithm all the time to serve you better ads in the future. So these two steps can be very stuck together, but you'll see that they're quite distinct in the code, you know, and there's a consistent pattern to this machine learning code where you use a function called fit to do the training. You fit the model to the data. So there's another synonym for training. You fit the model to the data. And then for the prediction phase, the inference phase, sorry, you use a function called predict. And that's the same in R and Python. So whichever language you're using, it's the same words pretty much. Okay. So there are two distinctions that I want to introduce: supervised versus unsupervised learning, and training versus inference. So if I could ask you all to execute this cell here. This imports a famous data set that's pretty much the data set everyone uses to teach machine learning. So you're not getting very innovative pedagogy here. I'm just teaching you the same way that I was taught. The scikit-learn package in Python comes with some data sets included to learn machine learning methods. And this famous one is the iris data set. And so this code gets the datasets library out of scikit-learn, imports the iris dataset, and then it prints the description of the iris dataset to the screen so we can see what's in here. So this dataset, it's a little mini database of 150 individual flowers that were measured in a laboratory. They're all species of iris. And there's 3 species, so there's 50 in each species. It's a very balanced data set. So there's 50 iris setosas, 50 iris versicolors, and 50 iris virginicas. And 4 measurements have been made of these irises: the sepal length, the sepal width, the petal length, and the petal width. So, and here's some summary statistics and some information about the data set, which you're more than welcome to read at another time. And if you execute this cell here, you'll see a little bit of the data. So first we see the 4 data points about each flower, you know, the sepal length, sepal width, petal width in centimeters. Here we can see the first 10 rows of the data. So you can imagine it like a spreadsheet. There's a spreadsheet hidden in Python right now, and each row represents 1 flower in the data set, and each column is one of the 4 data points that's been measured. So for instance, we can see that flower number 4, its sepal length, it had a 4.6 centimeter sepal, the width of the sepal was 3.1 centimeters. The petals were 1.5 centimeters long, and the petals were 0.2 centimeters wide. 4.6, 3.1, 1.5, 0.2. And down here, I've printed out the names of the first 10 species. The data set's not in a random order. It's all the setosas, then all of the other ones, and all of the other ones. So you'll see the first 10 flowers are all setosas, including flower 4. So you can see that for this data set, we actually can do either unsupervised or a supervised method. And that's what we're going to do now. First, I'm going to show you an unsupervised method, which just looks at the raw data in here and tries to find patterns. And then I'm going to show you a supervised method where we tell the computer, here's the information about each flower, and here's its species. Can you please learn to predict the species based on the input information? So we're going to be able to see both methods in play. Okay, this first step applies to both methods. And this is an important step. So when you train a machine learning algorithm, you always want to know whether the algorithm can be generalized or not. You know, when we learn something as humans, we learn it so that we can use it again in another situation. You know, there's no point learning that just this apple tastes good, because once we've eaten it, just this apple is gone. We want to know that apples taste good, so that next time I see an apple, I know to eat that and not to eat, you know, the bark off the apple tree, which tastes bad. You know, we want to be able to generalize from particular instances. One of the biggest problems in machine learning is that computers can be quite good at learning the exact pattern of exactly this data set you've given it, and then you give it a similar data set later and it gets everything completely wrong. This is called overfitting, or, you know, you could say overtraining or overlearning. Excessively, the machine gets too specific, too focused on this one data set. So we want to know, has the machine learned something general that will apply to all irises, or has it just learned some specific patterns that appear among these 150 flowers? The best way of doing this is to split your data into two groups. You're going to have some data which is for training, and you're going to use that to train the system. And then you're going to reserve some data which you don't show the computer, and you're going to test the model on that data. You're going to have training data and test data. Now, ideally, when you do this, you want the data to be shuffled. You want a random selection, so that as much as possible, the training and the test data represent the same group of items. If you randomly choose, then chances are they're the same. Whereas if you don't randomly choose, if you choose based on some criterion, then there's going to be, that criterion is going to distinguish the flowers in the training set from the flowers in the test set. So you want it to be random. You also want both of the sets to be balanced. So we've got three species of flower here. We don't want our training set to contain heaps of versicolor and our test set to contain none of the iris versicolor. We want a good mix of all three species in our training data and in the test data. And similarly, if you're doing machine learning in other domains, you would also want to shuffle up other features of the data points. You know, you might want novels 50. You might want a gender mix of authors in your set of novels, or you might want I don't know, a generous mixture of image sizes in a database of paintings or something. You want it all to be evenly shuffled. Okay, there's in this scikit-learn package, the machine learning package in Python, there's a neat little function called train test split, which does this for you. So that's what happens in this line. If you just press play to execute it, this train test split function, it takes the input data, which you can get by putting this this little line in here to get the data out of the iris data set. It takes the output data, the predicted the species of each flower as well. So that's like this iris, and then they use target for the name of the species, because that's the target that the machine learning algorithm is trying to hit. It's trying to get the species right. Here I've said how much I want to put in the training set and how much in the test set. It's very common to do what I've done here and to use 80% of the data for your training data and 20% for the test. Generally, the more training data, the better the model's going to be. So 80%, 20% is a good split. If you have a huge number of items, like 1 million items, you could do with an even smaller test set. You could put 95% of the data in the training data and just keep 5% for the test set. If you've got 1 million, but we've only got 150 here, so 80% is a good one. And this stratify argument says, can you please split the data up by whatever I put after this stratify and make sure we have an even number of these things in the training and test. So I've asked it to stratify it by the target, which is the species. So this stratify equals iris.target means that in our training set and in our test set, we've got a roughly equal number of all three species in both sets. You know, like there's an equal number in the training set of the three and an equal number in the test set of the three. And this step applies to both the supervised and the unsupervised. Right, so our first machine learning method. We're an hour into the course. We're up to our first method, which is k-means clustering. So I'm briefly going to just try and explain what this method does so you can get the algorithm. So k-means clustering, It's called k-means because it's an algorithm that sorts the data points into k clusters, and you choose what k is. You tell it, I want you to find 2 clusters or 20 clusters or 1,000 clusters. It clusters the data into k number of clusters using the mean. So how does it do that? Imagine we had a data set here, okay? And I'm just going to put some, oops, why won't that? Oh, come on, let me, there we go. Oh, why won't it? Oh, I can't do dots. That's really annoying. Okay, we've got this data set here with these data points. Okay, you can pretty clearly see that they fall roughly into 2 clusters, can't you? So maybe down here we've got, this is like, maybe this is plants again, and we've got like, you know, trunk width up here, and over here is like, you know, leaf length or something. So we've measured, in this case, 8 plants, and we've got their trunk width along the x-axis and their leaf length along the y-axis. And we say, I'm not sure how many species there. I think these might be 2 different species. Computer, can you try and sort them into 2 different clusters? So what this k-means does is it tries to come up with the average trunk width and leaf length for each cluster. And you've told it to find 2 clusters. So it's going to try and find 2 clusters. And in each cluster, there's going to be a particular average trunk width and a particular average leaf length. This is how it does it. Let me just change the pen color here. What it does is at the beginning, it's an iterative algorithm. It runs over multiple steps. So step 1, it just puts 2 random new data points in here. Oh. Why is that not? Okay, that's not working either. Sorry, this is not working anywhere near as well as I thought. Okay, it puts 2 random data points in here. Like this. Okay, which are called the centroids. And basically what these dots are, they represent the mean values for the 2 clusters. So this dot here will be, on the right, will be the average of one of the clusters, the average trunk width and leaf length, right? And this other one here is going to be the average for the other cluster. And at each step, this is what it does. First thing, it looks at each centroid and it says, well, it looks at each dot and it says, which centroid is this dot nearest to? So you'll see, for example, that this dot is clearly nearest to this centroid, and this one's nearest to this centroid, and this one's nearest to here. This dot, it's nearest to this left-hand one. This dot, it's nearest to this left-hand one. These ones are all nearest to this one. And then based on this judgment of which clusters the dots currently fall into, it then recomputes the average for these centroids. So you'll see, for example, this centroid on the left here, it's kind of not quite in the middle of all these dots that it's closest to. You know, if you take the average leaf length, it should be moving up a little bit. You know, because you can see most of the dots are above it on the leaf length axis. And if you take the average trunk width, it's going to move to the left a little bit. Okay, so you take the average of these 5 dots that it's closest to, and you move the centroid to where that new average is. So now, oops, oh, that's not going to. So now in the next step, you'll probably find it's somewhere up here. You know, it's moved up a little bit and to the left a little bit. Meanwhile, this one over here, you can see it's too far to the right, isn't it? If you take the average trunk width of these 3 dots, well, it's going to be sort of over here in the middle. And if you take the average leaf length, it's probably going to be a little bit lower. So it's probably going to move to somewhere like here. Okay, now the algorithm runs again. And you recompute which centroid each data point is closest to. So you find this one's still closest to this. These are all obviously still closest to this. But this dot has potentially changed cluster. It seems pretty equidistant now with the new centroids. I'm going to say it's probably closer to this one now. And this one here, it's still closer to this. These ones still obviously closest to this cluster. Okay, now with these new clusters, you recompute the centroids. And you'd find that, you know, this one here is probably going to move up a little bit, just a little bit to be, or it might sort of stay actually. It probably won't move very much. Let's just say it moves here. This one here is going to move quite far to the left because this dot's now fallen into its cluster. So you'll end up, this green one will probably end up somewhere over here. And then obviously on the next iteration, these two clusters are now, these two are definitely going to be in this cluster. And so you'll end up with a cluster like this and a cluster like that, you know, and once this dot falls out of the left-hand cluster, this centroid is going to move over here and you're going to end up with a centroid there. Okay. So I've had a question here where the centroids get placed in the first place. It's entirely random. It's basically random. It just picks a point within the maximum and minimum. Like it's not going to put the centroid up here because none of these examples of that have a leaf length that high. And it's not going to put it over here because none of the examples have a trunk width that wide. So it's just going to pick within the range of values. It's going to just pick random points. Some people have come up with some clever algorithms that make a good first guess of where the centroids could be to speed up the algorithm a bit. But basically, it's just random. It's completely random. The number of centroids dictated by the number of clusters you've decided to have. Yes. So one of the so-called hyperparameters of this model, one of the settings that you have to choose before it can do any learning, there's things that the model can tune itself, the parameters. They are namely the positions of the centroids. The model learns where to put the centroids. But a hyperparameter the human has to choose is how many clusters. So yes, it's called k-means clustering because you choose the k. Yeah, exactly. You have to decide how many centroids you want. I think when I show you the code, you'll see why it's not supervised. This distinction doesn't make much sense until you start looking at the algorithms. Basically, we know there's 3 species in this data set, so we're obviously going to choose 3 as the number of centroids. But we don't tell the algorithm the species of the dots. We just tell it there's 3 species and see if it will cluster them according to species or not. The reason it's unsupervised is we don't tell it which species each dot is. That's why it's unsupervised. When does it know to stop recalculating? Again, that's another hyperparameter. You choose the number of iterations. So I think in my code here, I haven't even selected it. By default, I think in this program, it does it 100 times. But you can choose. Is there a way of learning the most reasonable number of centroids? That's a good question. I'm actually not sure that I know the answer. But basically, with all these sorts of things, there's a lot of trial and error. So if you have some data and you think there's some sort of cluster to it, but you're not sure how many clusters to pick, the best thing to do is just to run it multiple times with different clusters. And there's various ways of evaluating a k-means clustering to see if it's come up with a good set of clusters or not. You know, the most obvious way is just to visualize the data, look at it and see, is this clustering real? You know, has it actually detected something real or is it just a sort of statistical artifact? But there's other ways of measuring how good a cluster analysis is, which you can look up. And so you might do trial and error. And since there are some criteria, if you were going to get the computer to learn the right number of centroids, basically the computer would multiple times run it with different clusters and then apply some evaluation algorithm you've picked until it settles on one that's good. So you could put a second algorithm on top that learns the number of clusters that's ideal. But by default, it's really something you pick. Okay, let's see how you do k-means clustering in Python. One thing you'll be happy to know is you don't have to describe these different steps. You don't have to tell the computer randomly generate centroids. See which data points are closest to each centroid. Update the centroids so that they represent the mean of that cluster. You know, recluster all the things according to the newly positioned. You don't have to do that. It's all done for you. So in this cell, what we see here is that from the scikit-learn package in the cluster module, you can import something called k-means. And then there's basically just 3 steps here. First thing is we initialize the model. So we create a new k-means model. And we're going to set the number of clusters as 3 for obvious reasons. And for purely pedagogical reasons, we're going to set the random state to be 1825. If you're doing this for research purposes, you may or may not want a random state set. All this does is the centroids are randomly allocated at the start. Computers actually can't generate genuinely random numbers. So they generate seemingly random numbers. But if you set a random state, then it's always going to come up with the same random number and the same allocation. All this random state 1825 is doing is making sure that all of us in the group get the same answer. If you deleted this, the code will still work, but we'll probably all get different answers. Okay, so you've initialized the model. And when you do that, you choose some settings. In this case, the only setting I've picked is number of clusters. If you look in the documentation for k-means, you'll see there's many other settings you can pick, such as the maximum number of iterations. You can pick all those sorts of settings. And when you create the new k-means model, you pick those settings. The next step is actually to train the data. So train the model on the data. So if you look up here, when we split up the training data, you'll see we ended up with 4 output variables. Okay, I've used X to denote the input data and Y to denote the species of the flower. Okay, the output, the prediction, the target. So you'll see we've got the training data, which is those 4 measurements for the 120 or so training items. We've got the test data, which is those 4 measurements for the 30 or so test items. We've got the training species, okay, which is the species for those 80 or so, 120 or so in the training set. And we've got the test species, which is the species for those 30 or so that are in the test set. Now, this is an unsupervised model. So when we train it, we don't tell the computer the species of the flower. We only tell it those 4 measurements. So when you look at this, you can see I've said, get my k-means model, fit it to the data, in other words, train it on the data, and all the data I'm giving it is those 4 measurements about each flower. So this is one way you know this is an unsupervised method, that you don't tell it what the species is of each flower. You just tell it, take these flowers, sort them into 3 groups, please. And then it'll go away and do that. It'll sort them into 3 groups. It has no idea what those groups are. And the groups may or may not have anything to do with the species. We'll see. We'll see what happens. Then there's the inference stage. So this line of code gets the model, and I ask the model to do a prediction, which is an inference. So it's now computed the 3 centroids. So using this inference step, I say, okay, can you please output to me which cluster you think each flower is in? That's the inference. And I've asked it in the first step to do it on the training set, so we can see how well it did on the 80 flowers, on the 120 flowers that we showed it to begin with. You'll get the chance in a moment to apply it to the test set to see if it works beyond the, if this model has learned something it can apply to flowers it's never seen before. Okay, so let's just execute that cell. Okay, you'll see k-means is very computationally efficient. that just did 100 iterations in like a couple of milliseconds. So that's one nice thing about k-means. It's very easy for a computer to do. Many machine learning algorithms require very powerful computing architecture to do, but not k-means. Okay, so then execute the next cell. The next cell just visualizes the data and shows you how well the k-means did at clustering it. So first, let's have a look at the graphs, and then I'll have a bit of a talk through the code, and then you can have a go in the next cell of modifying the code so it applies to the test set. So here in the graph, on the left, you can see the clusters that the k-means algorithm has sorted the flowers into. And on the right, you can see their actual species. So we can compare the two to see how well the k-means algorithm's done. Now, one question that may be in your mind is, how am I graphing them with only 2 axes when we've measured 4 things about each flower? You know, in my silly Google Jamboard example here, there were only 2 variables, so there were just 2 axes. We've measured 4 things about each flower, so actually I would need somehow to draw 4 axes and then put the dots on 4 axes. There's various solutions to this. I've picked a sort of cheating solution where I've used a method called principal component analysis, which basically just squashes those 4 axes onto 2 axes. And explaining that algorithm goes beyond the scope of the course. Don't worry too much about it. The only reason I've done it is so that I can make these 2 graphs down here. That's the only reason. So you'll see I've created a new set of x values called train x reduced, which have number of components 2, which are squashed onto 2 axes. You lose a lot of information about the flowers, but you keep a reasonable amount, so you can at least see them on a graph. So don't worry too much about that step. That's just what I've done in order to display them on a 2D graph. And down here, I've used the pyplot to create 2 graphs. So you'll see here, the first one is this scatter plot that compares, it puts it puts dots for each flower based on this reduced version of the training data. And then it colors them based on the predicted cluster from the k-means algorithm. So you see here, I put train x predictions, and that's the variable that records which cluster the model thinks each flower's in. So down here, I've colored with a C, colored the dots according to the predicted cluster. So there are the 3 predicted clusters. And then the second graph colors them according to their actual species, which is this train y variable, you know, which we got from up here. Train y is the actual species of the training set. Okay, so now it's your turn. Here in this cell, I've given you the framework for the code we've got up here. You just need to copy my code here, but change it so that instead of applying to the training data, it applies to the test data. So how do you do this? Basically, if you go through this code here, and every set where you see the word train, you replace it with the word test, that should work. And the reason is that specifically, I called the test data, you know, instead of calling it train X, I called it test X. Instead of calling it train Y, I called it test Y. So if you go through, starting with this line of code, and then going through here, and you replace everywhere you see train with the word test, and put in the corresponding spot here, you see I put a none everywhere where you need to write your own code. Then you'll be able to generate exactly the same graphs as this, but for the test data. So maybe I'll just give you 5 minutes to do that. So if you can see the cell I'm up to now, you'll see that it's got all these blue words none. And basically the task is up here. We applied our k-means model. After training it, we then used it to cluster the training data, which it had already seen. But earlier on, we reserved some data for the test set. So basically, I want you to rewrite this code here so it applies to the test data instead. And the way to do that is basically to look at this code here, and everywhere you see the word train, just replace it with the word test, and then the code will work. So let's just go through the answers. So test X predictions, how would we do that? So we get our k-means model, and we use the predict method, and we apply the predict method to test X. That's exactly right. Okay, so now this is going to use the centroids that it's learnt on new data to tell us which cluster each of the test flowers fall into. Okay, now this line, okay, this is not really learning. This is just this this PCA thing, just purely for plotting. PCA has other uses, but that's the only reason we're using it today. So it's number of components, we want 2 so that we can just have 2 axes. And we're going to use this fit transform method. And we need to do that on test X. Okay, so we're reducing the test data from 4 data points to 2. Okay, now down here, so I'm actually just going to copy and paste. Okay, so I didn't really explain this before. So this test X reduced, we've squashed it all down into 2 columns. We've taken the 4 columns and squashed them in 2. And when we graph something, we always want some X values and some Y values. So we're using the first of those 2 columns, which is column 0 for the X values, and the second of those 2 columns, which is column 1 for the Y values, to put dots on the scatter point. That's what's happening there. And then to color them for the k-means clusters, we use the test X predictions to color them with the C, this C keyword. Okay, and then this last line kind of writes itself if you got that first one there. Right. Okay, and then we'll just execute that. Okay, yeah, and it's you know, it's actually done pretty well on the test data. I'm really sore that this stupid random state thing hasn't worked correctly. I don't know why it's now not the same on everyone's screen, but anyway, that's the problem with doing machine learning. Okay, so what's people's impression? Has this model worked well? Yeah, it's worked really well. This is a really basic algorithm, k-means. It works using very simple mathematics. It works using, like, you know, year 9 mathematics. You know, you can take the mean. I think most of you can take the mean. You could do this by hand. It would be quite long, but you could do it by hand, and it doesn't use any fancy calculus or probability or anything. And it's quite robust and works quite well. You know, and there's a few other simple machine learning algorithms that also do good work. So if you want to cluster data, k-means works pretty well. But it does have some limitations. Okay, basically what it can be used for is to sort data points into clusters. That's all it can do, which might be what you want, but if you want to do something else, it's not going to do it. A different kind of machine learning algorithm, which you've probably heard of, it's a supervised algorithm called an artificial neural network or a deep neural network. It can be applied in many, many more ways to do many, many sorts of things. And that's because mathematically speaking, a neural network is a general way of representing any function. So anything that can be represented as a mathematical function can, in theory, be learnt by a neural network, any function at all. So as a result, neural networks find applications in all sorts of areas to do all sorts of things in all sorts of ways. Anything that can be reduced to a mathematical function. But they're also much more complex. So in this course, I'm not going to try and explain to you the back propagation algorithm that I mentioned before. It's to explain it, I'd need to go through partial differentiation, you know, university level calculus, and also give you an introduction to linear algebra, which is not something I can do just in a few sessions. And I'm not really the right person. You need a mathematician or a computer scientist. That is not the behavior I would have expected. He's changed the number of clusters to fewer clusters, and it still seems to be doing the same thing. Yeah, I can't explain that. It shouldn't do that. I don't understand why it's doing that. I mean, it doesn't do that for me. It's just done. If I change that to number of clusters 2, it keeps them as 2. Maybe you got confused because on the left here is the clusters learnt by the algorithm, and on the right we're just labeling the dots by their actual species from the data set. So that will never change, the one on the right, because that's just in the data set. Yeah. Okay. Right. Okay, so basically, I'll give you just a picture of what a neural network is, though, so that you can generally understand kind of what the code's doing. Basically, a neural network works like this. Imagine we're looking just at one flower at the moment, just one flower. Okay, I realize that I don't think this is what irises look like. This is more of a daisy, but we've just got one flower. Okay, and we know 4 things about it, don't we? Okay, we know it's you know, which I'm just going to call x1, x2, x3, x4. We know these 4 things about it, which are its sepal length and petal and sepal width and petal length and petal width. Okay, so what a neural network does is this. It's called a neural network because it's vaguely based on the structure of the brain. And it's made up of these neurons, and the neurons happen in layers. So the first layer of neurons takes the input, okay? And basically by passing the data through these neurons, it arrives at some decision at the end as to what it's looking at. So let's say in the first layer we had 3 neurons, okay? So I'm going to represent them by these circles. What each of these neurons is, all this neuron is here, okay? Each neuron looks at all 4 of the input data points. Oops, I didn't mean to do that. Okay. And all a neuron is a set of numbers. So let's call the output of this number 1 neuron A1. I'm just going to call it A1, and I'm going to say it's equal to some number times x1 plus some other number times x2 plus some other number times x3 plus some other number times x4, and then there's also it also just adds a constant, just a that's not times by any of the x's, which is the so-called bias, which is why I've called it a b. So that's what this neuron is. It's just a set of these 5 numbers, these 4 coefficients w, which multiply the incoming x values, plus some other number. So each neuron is 5 numbers, okay? And it multiplies the x values by all of that plus b, and then it just sums them all together and outputs a number. I'm skipping a few steps here. It then does another function to it for various reasons, but don't worry too much about that. And of course, you can then just duplicate this, okay? And you'll see that the first layer of this network, which has 3 neurons, it just means that it produces these 3 numbers, A1, A2, and A3, okay? Which are the activations. I've used A for activation, which are the activations of these 3 neurons. So each of these neurons looks at each of the 4 x values, multiplies them by some set of numbers that it has inside it, plus b, adds them together, and it outputs this new number. And you've got 3 neurons. So at the end of layer 1, when you've looked at this one flower, you started off with 4 numbers, which were the 4 measurements of the flowers. Now, after these 3 neurons have looked at it, you end up with 3 new numbers, which is each of these neurons' opinion expressed as a number of what it's seen. Okay, and then you might have another layer. Okay, so let's say in this layer there was 2 neurons. Okay, what happens is that each of these two neurons, it's now going to look, each of them is going to look at the 3 pieces of information from the previous layer, right? And both neurons do this, okay? And you're going to end up with something very similar to this at the top. You're going to end up with another set of numbers, except there's just going to be 2 of them, okay? Because there's only 2 neurons. And instead of looking at 4 X values, okay, they're just going to look at the 3, the A1 and A2 and A3 from the previous layer. So this neuron here, it's going to look at A1, A2, A3, multiply them by something, add a bias, and then sum them into a new number. And this neuron here, it's going to look at A1, A2, A3. It's going to multiply all those 3 numbers by something, add them together, add another number, and output a new number. So then we've got, at the end of this layer, we've now reduced it to just 2 numbers. And then there might be a final neuron, okay, which then a final neuron might look at those 2 and then output the final output. Now, where do these W and B come from? At the beginning, they're random. Exactly. When you create a new neural network, you choose how many neurons and what architecture they have, how they fit together, how many layers and whatever, what sorts of neurons. And then the computer randomly picks a whole bunch of W's and B's. And then the learning algorithm looks at all the flowers or whatever else and progressively adjusts these W's and B's, which are the internal parameters. And over time, it learns these neurons, it creates a set of neurons which is capable of doing something with the input data. So in our case, obviously, we want it to predict the species. That's what we're trying to do. But there's all sorts of other things you could do. Now, as I say, I can't just step through the learning algorithm like I did for k-means. K-means has a really simple, elegant learning algorithm. The learning algorithm for neural networks is actually, like all things mathematical, it's sort of elegant, but it's too hard to explain in this short format. So you'll just have to take me on faith that using this so-called backpropagation algorithm, the computer is able to look at one flower, come to some conclusion about it, compare its conclusion to the truth. This is a supervised method. So it predicts the species, looks at the real species, says, am I right or wrong? And if it's wrong, it's able to work out which neurons were to blame and adjust them. These W's and B's remain constant. It depends what you're talking about. During training, they're going to change because each time the algorithm goes through this loop of predicting a bunch of flower species and then correcting its parameters when it's wrong, it's going to alter the W's and B's. So in that sense, they will change. But when you're doing an inference, when you've trained the model and now you're applying it to a flower because you're not sure what species it is, then the W's and B's are all going to stay the same. It's just going to use those W's and B's to determine what the flower is. So whether they change or whether they're constant depends on whether you're talking about the training step or the inference step. This is not a clustering algorithm. It doesn't cluster them. Okay, it's not trying to infer that. It's actually trying to we tell it what species each flower is, and then it tries to give you a probability that it's that species. Let me add something to the end here. So I've explained sort of how the neural network tries to process the input data, okay, using these sorts of equations like this, okay. So it just takes the input data, multiplies each data point by some number to produce a new number, and then later layers of the network look at the outputs of the previous layers rather than looking directly at the flowers.
Yeah.
Okay, when it gets to the end, what it outputs is this. So we know there's three, in our case, there's 3 species, okay? There's species 0, species 1, and species 2, okay? And we've got, in the data set, it gives a label that a human can read for each of those numbers, but all the computer knows is that there's species 0, species 1, and species 2. At the end, in this particular problem, it uses a special function called a softmax function, which processes the final output of the network and transforms it into a probability. So what it'll say is it'll say something like this: we'll get three numbers, okay, like this. Okay, so let's see if you can sort of guess how this works. Typically, neural networks do express their result as a so-called confidence. In other words, which is a probability. Yeah. So this example, you'll notice the numbers add up to 1. Okay. Probability has to add up to 1 because that means something is happening. There's a 100% chance something's happening, so they all have to add up to 1. But the probability of each thing is different. And in this case, yeah, it thinks number 1's the most likely. And then a human would come along, and you'll see there's actually a line of code where we come along and we use a so-called argmax function, okay, which says of these three, it refers to these as arguments. That's confusing. Of these three numbers, which one's the maximum? And the argmax function would spit out 1 because it sees that 1 has the highest probability. And that's how we get from this probabilities to a prediction. We apply an argmax to this, and then that tells us the computer's predicted that this flower is species number 1, because that's the one that had the maximum probability. Questions? Is it okay to say that the W and B are meant to help the algorithm produce a better outcome? Exactly. That's it. The algorithm adjusts its W's and B's on the training data until it's able to predict most of the time what the flowers are that it's looking at. That's exactly right. So it just adjusts them until it can get to the right outcome. The W's and B's have no meaning of their own. They don't mean anything. They're just a set of numbers which allow the computer to map the input data onto the output data. They're like a bridge. You know, they're just a bridge that bridges from the input to the output data. And actually, you can never really interpret them. This is one of the criticisms of neural networks, that inside them, they just have millions of these numbers. Okay, that GPT-3, remember I read it's had 175 billion parameters? That means it's got 175 billion W's and B's inside it. No human can look at that and extract any meaning at all. So they're quite impenetrable. That's different to a k-means algorithm, because you can look at the centroids and you can see, oh, cluster 1, its sepal width is on average 1 centimeter and its petal width is on average 3 centimeters, because each cluster has a set of means that describes it. So you can interpret it as a human. And next week, we're going to look at topic modeling using Bayesian networks. And Bayesian networks can also be interpreted by a human. Neural networks can't. This is one of the great challenges. And people have come up with clever techniques to try and unpack the internal structure of neural networks. But they're all kind of indirect and clever techniques because intrinsically, they're not very interpretable. These are linear functions. It's exactly like your y equals mx plus b. It's just that y equals mx plus b is for just a 2D graph. If you add more axes, you end up with y equals w1x1, w2x2, w3x3, until how many x's. And depending on what you're looking at, if your input thing is an image and the image is 1,000 by 1,000 pixels, that means there will be 1,000,000 incoming x values. Oh. So there'll be 1,000,000 W's in each neuron in the input layer for each pixel of the image, and each pixel might be 3 numbers because it's a color image. So you'd actually end up with 3 million x values to represent an image. Yeah. So the point of a neural network is to they mainly find their application when they're processing a large amount of data, where you have a known outcome, and the point is that you want something that will classify or predict the data effectively. Unfortunately, it might not explain to you its prediction. So you need to then interpret it and analyze it and see whether you think it's working. It's quite different to most of the time in the humanities. Most of the time in the humanities, what we do is rather transparent. You know, we have something in front of us that we're interpreting. Okay, so we've only got 10 minutes left. So I just want to give you some code that lets you use a neural network. If we go back here, Google's produced this amazing free framework for doing neural networks called TensorFlow. It contains a module in it called Keras, which gives you a way of programming very simply. Okay, if you get really deep into neural networks, you'll probably stop using the Keras code and you'll dive in a bit deeper and use different, somewhat more complex code that lets you adjust things more. But when you're starting off, this Keras code lets you build and test neural networks very quickly and easily. And I've also imported a specific part of that, layers, which makes it, again, a little bit quicker to write the code. So the pattern is very similar to above. Above here, we initialized the model with some settings. Then we trained the model on the data using the fit method. Then we applied the model to the data using the predict method. It's exactly the same for this. So the first thing is we're going to initialize the model. For this kind of basic neural network, which just has a series of layers one after the other like this, you can use this keras.sequential because they're just a series of layers in sequence. There's more complex networks which have different sorts of connections where the sequential doesn't work. But for a basic network like this, we do this. This simple sort of layer where every single neuron is fully connected to all the previous ones. So like all three of these neurons are connected to that. All three of these neurons are connected to that. All four inputs go into this neuron. All four inputs, it's so-called fully connected. To do that, you use a dense layer. So here we have 3 layers, okay? The first layer has 10 neurons. The second layer has 5 neurons. And the last layer has 3 neurons because these fall into 3 species. Okay, so you have to choose 3 neurons. And then I've added an extra argument here that says activation equals softmax. And that specifically asks the computer to output something like this, 3 numbers that add up to 1 to represent the confidence that has in which species this flower is. Okay, so that's how easy it is to define a new, you can sub in different sorts of layers, change the structure of each layer, and it'll just build the network for you. All of those complex W's and B's and everything, it's all taken care of, and it knows how to train it and everything. It's really brilliant. Okay, so we initialize the model, then obviously we need to train it. Now with TensorFlow, there is one extra step in between the initializing and the training, and that's this so-called compile step. And at this point, you need to give it a bit more information about how you want it to train itself. So you choose a training function, which is also sometimes called an optimizer. I've picked this Adam, which is a popular training function. There's many to choose from, and I can't go into what makes them different this time. You also need to pick a loss function, which is the function it uses to work out whether it was correct. Okay, and for this sort of situation where you've got 3 categories or 4 categories or 5, the correct one is called this sparse categorical cross entropy. Categorical is the key thing there. It's sorting them into categories. And finally, you can optionally tell it to give you some information about how the model's doing each training step. So I've asked it to tell us the accuracy each time. How accurately is it predicting the species of the flowers? And it'll tell us that for each training step. You'll see it prints out nice information. Once I've done that compile step, I can do the fit step. Now you'll see a big difference here between the previous model and this. It's because this is a supervised method. So in this case, because it's a supervised method, we don't just give it the information about the petals and sepals, okay? We also tell it what species each flower is. And in this case as well, it's at this fit stage, we can tell it how many times to look at the data. So 1 epoch means it's looked at every flower in the training set. That's 1 epoch. So I've told it to go through all the flowers 100 times. Neural networks need a lot of iterations to get right. They take a long time to learn. They learn very gradually. Okay, so you can press play and you've trained your first artificial neural network. And it's told you, just here, you can see each training epoch. It takes 2 milliseconds per step for each epoch. It divides the flowers into batches of 32. It takes 3 milliseconds or 2 milliseconds to look at one batch of 32 flowers. That's pretty cool, isn't it? And you'll see now, you probably might all have different results to me. So my one got to an accuracy of 95%. If I could explain to you the learning algorithm, this would make sense to you. Basically, imagine, okay, so this thing, it has several thousand parameters, and they can be anything from 0 to 1,000,000 to 1,000,000,000, whatever, or minus numbers. They can be anything. They can be 1.3, they can be 1.300007. They can be anything. Now imagine how many possible settings for those parameters there are. Trillions and trillions and trillions of possible settings. And the algorithm searches through all the possible settings till it finds one that works. Okay, and there's a large degree of randomness there. And generally, if you train a network long enough, generally speaking, it should converge on a good result, and you'll end up with all networks being pretty similar. You know, all the networks you might train on the same data with the same architecture would all be similar, but there's always going to be some differences. Okay, so if you execute this cell, you'll see a replication of the above graph, but using the neural network, and you'll see that it does quite well as well. And there's a big difference here, though, which is that the colors on these two graphs are always going to correspond, because we told it what species these flowers were in the test set, in the training set, sorry. Okay, we've only got 3 minutes left. So I did want to get you to do this code yourself, but maybe I'll just step through it. So there wasn't much coding in this session. There's going to be more coding in the future sessions for you to have a practice with. But basically, just here, you'll see there's, again, something very similar to the k-means, and then something in addition on top. So to get the output of the neural network on a set of flowers, you again use the predict method, then with the input data, and it'll give you its output. But its output is going to be like this, little sets of 3 numbers, which is not so useful for us because we actually just want it to tell us which species each thing is. So you have to do this, as I said, argmax step. So you'll see that this first variable I've called trainx neural probabilities. That comes out of the predict method. If I want the predictions, like it to tell me which species it thinks each flower is, then I use this from the numpy library. I use this argmax function. I put the probabilities in, and I need this axis equals -1 method. Don't worry too much about that. Just know that you need it. So that will then turn those probabilities into which species it thinks each flower is. Of course, one nice thing about this neural network, unlike the k-means, is it will tell you how confident it is that each species is a particular species. So if you looked at the actual probabilities, you'd probably find that here on the edge of these two closely related clusters, the probabilities are lower. Its confidence is lower because it's not sure. That's one nice thing about neural networks. It gives you this confidence. Okay, so you could do exactly the same for the test data down here. And, you know, actually, rather than showing you, maybe if you want, you can do that in your own time. But you'll see it does quite well on the test data too. And you've got the code there that you can copy and play around with if you wish. The last thing I was going to talk to you about was accuracy, precision, and recall. But we've run out of time. Maybe I'll cover that at the beginning of next week. Actually, precision and recall aren't really relevant to any of the models we're looking at later on. It was just to explain to you that there's different ways of evaluating how well a bit of machine learning's gone. The accuracy is not the only way of measuring it. And sometimes you want to measure it in other ways. So I might go through that next time. It'll only take 10 minutes. But right, that brings us to the end. So if you're interested in some of the different kinds of algorithms there are, I've given you some links here in this section of the notebook you can look at. But I just want to skip ahead to the conclusion to just cover what we've looked at today. So we began by looking at the relationship between machine learning and artificial intelligence. And then we went through some of the big concepts that divide up the different sorts of machine learning algorithms. So we looked at supervised versus unsupervised learning, with the biggest distinction between different algorithms. Then we had a look at some of the practicalities of implementing a machine learning algorithm in Python. Firstly, the idea that you need to split your test and training data so that you have some training data for the model to learn on and some test data to test whether the model's worked and can generalize from the training data. Then we looked that different models have different sorts of settings that you can choose. So typically in Python, you begin by creating the model and choosing some hyperparameters, such as in a neural network, the number of layers and how many neurons are in each one and so on. Or in k-means clustering, the number of clusters you want it to try and find. Then there's the training step, which normally uses this fit method in most machine learning packages. And there's a bit of a difference there. In an unsupervised one, you train it just using the input data. And in a supervised method, you also provide it with the labels or the answers or whatever, the target, the predictions for the training data. In our case, that was just labels, you know, species 0, species 1, species 2, but there's all sorts of different things you can have. You know, it really depends on what sort of data you're dealing with. It's not always just labels like that. Depends. For instance, if in the Google Translate example, the input data is the original sentences in Bengali or whatever, and the output data is the translation of those sentences in English. You know, so that's what it is. It has to move from one of those to the other, and then it needs a way of measuring how close its translation is to the real translation. It's a bit complex, that one. But there's the big difference between supervised and unsupervised in the code. And then finally, there's the inference step where you get your trained model and you apply it. You know. Okay, I hope that was easy enough to follow. You've now successfully implemented 2 machine learning algorithms, k-means clustering and an artificial neural network, in only a few lines of code. So you can see that there's been so much development in this area that it's actually not that hard to get started with the actual machine learning part. You know, the hard thing is knowing what to do, like what data to get and which sort of algorithm to pick and how to get it all fitting together. The actual just using the machine learning algorithms is quite simple. All right, well, I'll see you all next week for our next algorithm, which is topic modeling.